Welcome everybody to the study seminar, and I think it's been 2 years since last time we have an in-person seminar, so it's really great to finally come back in person. And today we have my greatest pleasure to introduce our speaker, Byol Kim from Biostudy Department. Byol get her PhD in University of Chicago at working with Rina Barber and Mladen Kohler. And I think many of you probably have read a lot of papers from these two persons. And today she's going to talk about a very exciting topic about how to do black box tests of the algorithmic stability. And let's welcome Byol.
Hi. So happy Friday afternoon, everyone. It's amazing to finally meet everyone at the Department of Statistics. And I would like to thank Yantu for his kind invitation. As you've just heard, I'm Byol Kim. I am currently a postdoc over at the Department of Biostatistics. I work with Ali. I recently became a postdoc in the UW Data Science postdoc as well. And not so long ago, I was a PhD student at the University of Chicago, and I was fortunate enough to be advised by Rina Barber and Mladen Kohler. Today, I'm going to talk about a project I recently completed about the about limits of black box testing procedures of algorithmic stability. So I'm a little nervous because, for one thing, this is only the second time that I'm giving this talk. And for another thing, this is my first in-person talk in 2.5 years. And it's just like hitting me that I have an actual audience in front of me responding. So I am a little unsure of how this is going to go, but I guess I'll get through this. So I came away from this project feeling like I have a lot more questions than any satisfying answers. So I'll be really looking forward to your feedback at the end when I'm through with all of this. Okay, so here is my motivation slide. So I don't think I'm making a hugely controversial statement by saying that machine learning predictions are increasingly becoming a routine part of our lives. Many of the success stories of machine learning has revolved around what we tend to call black box algorithms, such as deep neural nets or random forests. We call them black box because they are very difficult to analyze, and we don't really have a good grasp of what's going on, or whether if everything is happening as they should be happening. And if anything, the task of accounting for the predictive performance of black box learning algorithms is becoming more and more difficult, although we are getting more and more of these things, because the algorithms are getting more and more complex, and the model classes are also getting more and more complex. This is unfortunate because, as we all know, every model makes errors, and when such models are deployed in actual problems, they will be associated with actual costs. Keeping this in mind, one really solved requirement that you can ask of a learning algorithm is that when you give your learning algorithm similar input training data sets, you should be able to get out models that are making similar predictions. To put this another way, I feel like most of us will find it really hard to trust machine learning predictions if we knew that they were produced by a black box learning algorithm that was giving very wildly different answers for very similar input data. So many people have actually studied the connection between algorithmic stability and the generalization performance. And this was mostly done in the field of learning theory. The earliest works in this vein dates back to 1970s. And then perhaps the most influential paper on this topic was by Busquet and Elysiak in 2010. And their work was hugely influential in how people think about this problem. More recently, and what these works in learning theory have found is that you can use algorithmic stability to derive guarantees on predictive performance of some arbitrary learning algorithm. And what's cool about such bounds is that they don't necessarily depend on the complexity of your model class. So it seems like a notion that's independent of the model class, and like that depends only on the algorithm and the data distribution. More recently, in the area of distribution-free predictive inference, people have found that you can use algorithmic stability as a condition for deriving guarantees of some inferential methods that make no additional assumptions on the distribution. So the papers that I have in mind are papers like one by Steinberger and Lee in 2020, and one by Barber et al. From 2021. And these are papers that study the distribution-free validity of JACnet prediction intervals, which are prediction intervals that you construct using leave-on out residuals. So the moral of all this is that if you're able to accurately measure the stability of some black box learning algorithm, then you can use the knowledge to obtain guarantees on the predictive performance. However, by definition, it is very difficult to measure the stability of your learning algorithm. In fact, there are many works that have studied the algorithmic stability properties of a particular learning algorithm, but this was done mostly in the white box setting, where you know / able to analyze the inner workings of the algorithm. And there hasn't really been work on analyzing this in the black box setting. So this raises the natural question. If all you're able to observe is, well, you can observe you can make changes to the input data set and then observe what kind of changes it produces in the output predictions, then can you still make accurate inference about algorithmic stability based on these empirical observations? In the remainder of this talk, I am going to first give a formal definition of black box testing procedure. And then I will present a very simple black box testing procedure. This procedure is not meant to serve as like a practical procedure. The point of this will be to illustrate the difficulty of this problem. And this will be done by presenting another bound on the power of any black box test that has certain assumption-free validity. And by showing that this bound is obtained by the simple black box testing algorithm, I'll illustrate the difficulty of this task. And I'll finish this talk by discussing some future directions. Okay. But first, in the next couple of slides, I'm going to describe the formal setup and also give the mathematical definition of algorithmic stability that I'll be using in this talk. So the setup is a supervised regression setup. We assume that each data point comes in the form of a feature response pair. So X represents the features. I'm just like really bad at pointing this. And then Y represents the response. And the interest is in predicting Y given X. We assume that the data is independent and identically just distributed. And what we do is we take n independent and identically distributed observations forming a training data set. and then give it to some learning algorithm. And then this learning algorithm learns a model for making predictions. We're going to use letter A to represent a learning algorithm. We can think of this as a map from the space of all data sets of any size to the space of maps between X and Y. A somewhat important point is that we only assume that X can be represented as a point in RD and Y can be represented as a point in R. But we make no further assumptions about the support of X or Y. So it's just some probability distribution supported in RD. An additional assumption is that A is a symmetric learning algorithm. This just means that if you shuffle the indices of the training data points, then this makes no change in your output. You get the same model, you get the same predictions. And our conclusions are going to be the same without this assumption, but many algorithms that are used in IID setting are indeed symmetric for one thing. And I wanted to point this out because actually like many of my notations make this assumption. So if you want to remove this assumption, you have to change certain things. The definition of algorithmic stability that we are going to use in this talk is this following notion based on removing a data point. So suppose I have a pile of data. I have n different points. I feed it through this black box learning algorithm A, and then I get a model mu hat of n. And then I remove a point from this pile. Again, feed the pile of data through the black box algorithm A. This gives me another model mu hat of n minus 1. And the idea is that if algorithm A is stable, then mu hat sub n minus 1 should not be that different from mu hat sub n, because all I've done is remove a very tiny portion of the data pile. Therefore, I measure stability by measuring the change between the two models. So the formal definition is this: let epsilon be some positive number and delta be some probability. We say that a symmetric learning algorithm A is epsilon delta stable with respect to training sets of size n from the distribution P if the probability that mu hat sub n evaluated at xn plus 1 and mu hat sub n minus 1 evaluated at xn plus 1 is not more than epsilon apart. Well, probably that it is more than epsilon apart is bounded by delta. And here the probability is respect to all randomness. So more compactly, we see that the triple APN is epsilon delta stable. So epsilon delta stable is a property of the triple. You might wonder if it's possible to define stability in a slightly different way. And it is indeed possible. And there are many different variations of this theme in the literature. So there's this paper from 2002 by Kutin and Niyogi that goes through at least 12 different definitions of algorithmic stability alone. And then, of course, subsequent papers just kept adding to the list of definitions. So the list is now significantly longer. The basic idea that they're trying to capture is the same. This is that you should measure stability as the amount of change in the output induced by some change in the input. How they differ is in how they define, in the kind of perturbations to the input that they consider, and how they define the change in the output and how they quantify it. So for example, here I have considered stability with respect to removing or adding a point, but you can also consider stability with respect to replacing a point with a freshly drawn point from the same data distribution. Also, I am measuring the change in the output by comparing by measuring the distance between two predictions from two different models. However, one notion that's really popular in learning theory is to compare the model losses induced by the change in the input data. And I've also seen a conformal prediction paper that was defining stability in terms of the induced change in the conformal discourse. In our definition, we look at what we look at is we define an unstable event parameterized by epsilon, and then we look at we check whether this probability is small, where small is defined by delta. What you can also do is you can look at the expected value of the change in the output. That's been done before, and that will lead to another variation of the problem that we are going to look at in this talk. But finally, I feel like another really popular notion has been to look at a uniform bound. And by uniform bound, I mean that this has to do with uniform stability. Uniform stability is the notion of stability that defines stability with respect to the bound on the change, well, bound on the different size of the difference of the two predictions. But then this bound has to apply uniformly over every possible sample of size n and every possible value of the feature. So I felt like I had to mention it because it's just really popular in learning theory literature. But this last notion is unfortunately not applicable to our setting, because then that kind of stability is only a property of the learning algorithm, and it has nothing to do with the data distribution. Finally, our definition was used in Steinberger and Leib and Barber et al. To prove distribution free validity of jackknife prediction intervals. That notion is closely related to hypothesis stability in Busquet and Eliziev. Okay. Next, in the next several slides, I want to first define the notion of assumption-free validity, and then I'm going to formalize the notion of black box testing. Mm-hmm.
So in your definition, the constant function that estimated that maps always to 1, that's 0, 0 stable.
Yes, that's very stable.
So therefore, epsilon delta, having small epsilon delta does not mean that the estimate is good, because it could always match to 17, and 17 is always 1.
Mm-hmm.
So are you going to use your definition of epsilon stable to kind of say that this is a good estimate, or just you can't do that? You can't say
yeah. So right. So stability is like it's like a separate axis from whether your algorithm is good or not. Yeah. Obviously, the ultimate stable things algorithms are the ones that are like completely ignore the data and just output constant things.
Let's ask a related question. So in terms of like the different definitions, is there a way to think about them in terms of like a decision theory interpretation? So like the loss in terms of if you're wrong with one definition or another. So like if you take any draw, are you sort of hedging against like an average across all the sort of different possible ways that your model could differ across the data, versus like if you take one specific draw, you're hedging against the sort of worst case or something? Is that kind of the way to think about it? I'm just trying to get an intuition for why I would use one notion of stability versus another.
Oh, that's really an interesting question. It's kind of in a different direction from where I'm trying to go with this.
Okay, so
yeah, we can definitely talk after. Okay, so here our problem is, can we test the null hypothesis of instability using just empirical observations? So let's just assume that we have bought into some definition of algorithmic stability. It seems sensible for whatever we want to do later on. So the approach that we take in this talk is hypothesis testing approach. So we use available data and then stuff that we get out of running the black box algorithm to answer this hypothesis testing problem. I am going to introduce a new notation, T star of epsilon delta. This is supposed to be, well, T stars of epsilon delta stands for the ground truth for the triple APN. You can think of this as an unknown function of the triple APN, where it takes the value of 1 if it's epsilon delta stable, and it takes the value of 0 if it's not epsilon delta stable. In this framework, we can think of a test as a database estimate of the unknown population parameter. So we are going to use t hat epsilon delta to denote any test. I'm going to write the test as a function of the learning algorithm A and the data sets curly D sub L and curly D sub Yale. So curly D sub L stands for the set of labeled data. The size of this data set is denoted by capital N sub L. Curly D sub Yale denotes the set of unlabeled data points. The size of this data set is denoted by capital N sub Yale. The idea is that in order to estimate T star of epsilon delta of A, P, N, you apply the test to the learning algorithm and the data sets that were drawn from the data distribution P. Given our motivation and setting, we want to focus on tests that satisfy the following notion of assumption-free validity. And this just means that for all algorithms and all probability distributions and all sample sizes, if the triple is not epsilon delta stable, then the probability that the test outputs a rejection is bounded from above by alpha. So it's just type 1 error control. Next, in order
just to clarify,
Mhm.
the epsilon and delta, do they depend on n or not?
epsilon and delta,
Are they epsilon n and delta n, or they are just fixed?
I think you can fix one. So here, what's
No,
happening
I
is
them to change with.
you can study the setting as well. But here what we are doing is we are going to fix n, and then we can just choose epsilon and delta freely.
So you are studying the finite sample case. So
Right,
n is fixed. Sample size is
right. You know, like the sample size at which you want to measure stability.
Okay.
Yeah, I mean, but definitely people have studied, say fixed epsilon or neither, and then have studied the behavior as n goes to infinity.
So maybe a follow-up to what Frank was asking. Suppose you have the AP and N are stable, that would imply something about N plus 1, right? And maybe some other delta.
So I am not making that assumption.
No, but it's not an assumption. It's probably something that is modeled from the stability of N.
Oh, I am just saying that, making the statement. So over there, I'm not assuming any sort of relationship from one end to the other. I'm just fixing a particular n, and I'm saying that the triple is epsilon delta stable if it satisfies that.
I'm saying that it would be implied.
Yes, but because this is,
It's not related to the hypothesis. I realize.
yeah.
It's standard. It's
Yeah,
not
I feel like, so I know why you're saying that, and sure, it could be implied, but then yeah, that's like a different direction too.
It's a different-
Yeah,
I thought-
yeah. Okay. So next is the definition of black box testing procedure. So in order to study the limits of black box testing procedure, we need a good formal definition of what we mean by a black box testing procedure. So at a glance, this looks obvious. I mean, we're in a black box setting. What we can observe is, well, I put in this data set and then this produced this kind of outcome. And then this is supposed to be the information that a allowable test, admissible test is going to work with. However, when you think about this is not going to be enough. This is because the test can cheat in two different ways. The obvious way is obviously because the test is actually picking under the hood of the learning algorithm A, and it actually has access to some or part of the calculations that are happening inside A. The other way is by performing an exhaustive search. So if you have a test that's actually mapping each sample to each model, and once it has a model, it's evaluating a model at every possible value of the feature in the feature space, then it's black box, but it's not really black box. So in other words, we want to include only those tests that can be written as a measurable function of at most countable number of predictions produced inside a testing algorithm. Although we do allow for the data sets to be generated inside a test, and then this doesn't have to be the original data set. Oh, and I thought I would just point out that black box testing is actually a terminology that's already in use in software testing. So it thinks what it means, what you think it means. It's a testing technique. It's a technique for testing a piece of code where the software engineer makes no assumptions about the internal structure, only about like what form the input can take and what you can expect from the output. And then you just plug in different values of the input, and then you check the performance by looking at the output. So I thought it's interesting that what we are doing seems pretty similar. We are doing a black box testing of a learning algorithm A, and the performance metric is it has to do with stability. So here at last is our definition. We say that a test is a black box test if it can be put in the following form for some suitable measurable functions and uniform random variables. So the measurable functions are, well, there's one, T. T is for computing the role of T is for outputting the final verdict of whether the algorithm and the data sets that, well, the probability distribution that you got the data sets from is absolute delta stable or not. The Fs are for generating data sets inside the testing algorithm. Uniform random variables are for capturing the random behavior inside a test. The test proceeds in stages, and these stages can be run either in parallel or serially, or a mix of both. At each stage, what you do is you generate a pair of data sets, one labeled and one unlabeled, as a function of everything that you have seen so far. And then you fit a model using the label part of the generated data set. And you evaluate the model that you obtained using the unlabeled part of the data set. And after you run all the stages, you aggregate the information from all different stages into a final estimate that's computed as a function of everything that you have observed. So I admit that this is quite a lot. Like the definition in the paper is actually even more complicated. The reason that we need a formal definition of a black box testing procedure is because without ruling out the rather trivial cases that were discussed in the previous slide, the mathematical problem becomes quite trivial. And on the other hand, we are also rolling out tests that we cannot expect to run in practice. So if we, without rolling out those trivial weird cases in which a test looks like a black box test, but it's actually not, we don't end up with conclusions that are useful from the point of view of practice as well. Okay, in the next couple of slides, I'm going to give 3 different examples of black box testing procedures to make everything more concrete. And then I'll also give some non-examples. So here is an example of a black box test. I'm going to call this a simple binomial test. This is by far the most important example. So please try to keep this picture in mind. It's not very good, I have to admit. So here is the idea. The idea is really simple. Let me see. Oh, here's a pointer. Okay, so the idea is to split up the available data into smaller data sets. And then small data sets, and each small data set contains exactly n labeled points and a single unlabeled point. You use the label part of the data to obtain 2 different models, mu hat of n and a model after removing one of the points. And then using the unlabeled point, you evaluate the distance between the 2 predictions. This is delta k. And the information from all different partitions is aggregated into a single test statistic, which I'm going to call B. And this is just computed by counting the number of times delta k exceeds epsilon. And if B is below some suitable choice of threshold, then you reject the null hypothesis. And if B is large, you accept the null hypothesis. This is obviously a black box test according to our definition. The final outcome depends on 2 capital K predictions, which are computed by making 2 capital K calls to the black box learning algorithm A and 2 capital K calls to the model evaluation method. The data generating mechanism is just data splitting. The next example is bootstrap samples method. And it's instead of splitting the data in the first step, I can instead sample replacement from the given pile to create small bootstrap samples. And then the remainder of the step is quite similar to the earlier binomial example. This is also a black box test for the same reason that the previous example was a black box test. And the only difference is that now it's using a different data generating mechanism. Here's another example that's slightly more general. So instead of using the available, well, I can use the available pile of data to estimate the data distributions themselves, and then simulate data sets from the estimated data distributions. And again, the rest of the step is the same. This is again a black box testing procedure by the definition, and with a different data generating mechanism. Yes.
Sorry if I missed this earlier, but what's the significance of the mu hat or mu hat n versus mu hat n minus 1 in the definition of S1 delta table?
So at this moment, the reason that I'm using mu hat n and mu hat n minus 1 is just because I'm looking at stability with respect to removal of a single point. But yeah, does that answer your question?
Oh, okay. So the idea is like, how does it change when you remove 1 point? So I guess how does that relate to like the binomial or the bootstrap? Would you like bootstrap and then bootstrap one less?
Oh, yeah, so there's like, this is really hard to see, but sorry, I keep missing my pointer. So I generate data set and then I remove a point so that it's like mu hat and mu hat and -1. It's like, okay, I have a definition of stability and then let's do the obvious thing in order to estimate that. Like, let's do the most naive thing possible for now. And that's this estimate. Okay. Our definition is flexible enough to have more sophisticated procedures. However, our definition does not allow tests, for example, tests that exhaustively searches over the input data space. For example, you cannot do something like, okay, I'm just going to look at every possible value of y. Well, I'm going to vary the y value of the last response point over every possible value of y and then compute the supremum. That's not possible. You are also not allowed to have tests that map out fitted models point by point by evaluating at every point x. Are there any other questions about the new definitions that I introduced? Because I'm going to switch gears and turn to theory.
I'm just curious, like I think you can also generalize the entire thing, not only to the prediction problems, right? You can also think of, I can imagine you can also apply a similar framework to, let's say, estimating the model parameter or something, because, and then you just do the same thing, do the sample splitting, and then you can also compute and let's say remove one example, or remove one observation, whether that will change your final estimate a lot or not. So then you, instead of using mu hat and x plus 1, it's just mu hat n minus mu hat n minus 1. I guess that can also, like this entire framework can also be generalized to other cases, right?
I think so, yes.
So in the same spirit, so the definition of stability is that you're using the epsilon delta stability. In some ways reminds me in the spirit of what you do in differential privacy, where the idea is the same, but rather than trying to do it for prediction in differential privacy, it's about the quality of the point estimator of the parameters. So maybe you want to leave this question for the end, and I'm happy if you want to do that. But maybe you're thinking what are the conceptual and practical connections between kind of differential privacy and what you're doing, I think would be interesting.
Yes, I fully agree. Yes, let's return to this later. Okay. Yes.
So maybe you are going to talk about this in the next part of the talk. But I'm curious, how do you use this test? Because you have to know in advance and delta angles on the same time to do this test. And if you have to use it to predict something about the generalization level of your view, you know epsilon and delta in advance, or you still only know one of them.
I think in our framework, what we have in mind is that you kind of have an idea of like an epsilon and delta that you want your learning algorithm to satisfy stability for. And then, yeah, so you just, at this moment, you just pick a random value, like I'm, okay, for this, for example, for this problem, I'm okay if the predictions don't differ by more than say 0.01 apart. So that's epsilon of 0.01. And then the probability of unstable event, I'm okay if it's within 0.1. And then that gives you epsilon and delta. And then I just use my learning algorithm. Well, if they're fixed, then there's no problem in checking whether my learning algorithm satisfies this epsilon delta stability. I don't have this on my slides, but because at least for the tests that I have given as examples, it satisfies a certain monotonicity property that, well, the whole problem has this monotonicity property that if, say, your algorithm is stable at epsilon and delta, then it has to be stable for all values of epsilon that's greater than this epsilon, and then all values of delta that's greater than delta. So you can actually use that to define an estimate. But then that's in the paper and like not on my slides. So yeah, that's a good question. But yeah, if you're actually interested in estimating certain epsilon corresponding to delta, whereas a certain delta corresponding to epsilon, then you can tweak stuff so that you are able to do that. Maybe that answers your question, maybe not.
I can ask you.
Yeah.
But maybe another way to use it is, so don't try to fix delta, but just construct the curve of basically what you're calling B in your previous slides as a function of epsilon. And maybe that curve can be used to compare algorithms in a scale that is different from accuracy.
Yeah,
And
that's what
there's
that's
very
those are
interesting.
dependent tests. So, yeah, of course, that's what I would do.
Okay. Oh. Okay, so it looks like I need to speed up a little. Okay, I'm going in the next several slides, I'm going to show that the simple binomial test has assumption free validity. So let's recall the definition of epsilon delta stability. Okay, I'm going to write delta epsilon star of A, comma P, comma N for this probability here. So this simplifies the notation a lot. And with the new notation, the null hypothesis of instability is just the statement that delta epsilon star is greater than delta. Now I'm going to give the exact details for implementing the simple binomial test. In the binomial test, we computed B as the number of times that the difference of two predictions, delta K, exceeded epsilon. To make comparison with a later result more easy, I'm going to write K as the floor of kappa, where kappa is the minimum of two fractions, capital NL over N, and capital NL plus NU over N plus 1. So you can verify that this is just the maximum number of independent data sets that you can create when you have capital NL many labeled data points and capital NU many unlabeled data points. By construction, B has binomial capital K delta epsilon star distribution for any probability distribution P and any learning algorithm A. And well, I should point out that what's happening is the distribution of B depends on A and P only through this unknown parameter delta epsilon star. And delta epsilon star is a function of A, P, and N. Now let K star be the alpha quantile of the binomial K delta distribution. And let A star be the difference between alpha and probability that a binomial K delta random variable is less than K star divided by the probability that binomial K delta is equal to K star. And you can verify that this is a value between 0 and 1. The simple binomial test is the randomized test such that it rejects the null hypothesis if B falls below K star. And it accepts the null hypothesis when B is greater than K star. And then it outputs a random decision according to Bernoulli A star random variable if B is exactly equal to K star. So here's an example for the case when alpha is equal to 0.1, delta is equal to 0.1, and capital K is equal to 51. So for this case, you can calculate that K star is equal to 2. So the probability of probability of the orange part is under alpha, and probability of the green part and orange part together is over alpha. So what you want to do is you want the test to reject for the for b less than or equal to 1. And then when b is equal to 2, you want to output a random decision to match the type of error rate. So the test clearly controls the type of error rate under the null. Now let's look at power. We can compute power for certain special cases. If delta is less than or equal to 1 minus alpha raised to the power of 1 over k, then in this case, you can verify that k star is equal to 0. So the test rejects the null hypothesis when when b is equal to 0 and the draw from the random the Bernoulli A star distribution takes the value 1. So in this case, the power is what is this? Alpha times 1 minus delta epsilon star or 1 minus delta raised to the power of capital K. If the above doesn't hold, then if delta epsilon star is equal to 0, then b is equal to 0 with probability 1. So the power is 1. So when can the first of the two cases hold? Suppose we have delta equal to 0.1 and alpha equal to 0.1. Then delta is less than or equal to 1 over alpha raised to 1 over k if k is less than or equal to 21. So this is the situation when the amount of data you have available for testing is less than or equal to 21 times the sample size n you're interested in studying. The result we have so far is summarized in theorem 1. So the first statement just says that the simple binomial test is a black box test that has assumption-free validity. And then the second part of the test says that if you have APN that is epsilon delta stable, then in these two special cases, the power of this test is given by this expression. However, the binomial test was really, it did not seem like that the test was using the data effectively or efficiently anyway. It seemed very naive. So the question is this the best we can do? And if you actually look at this expression, you are not expected to have much power if k is rather small and delta epsilon star isn't like drastically smaller than delta. The surprise, or perhaps the surprising part, is that indeed this is the best you can hope to do, if you are studying, or if you're looking at black box testing procedures with assumption-free validity. So theorem 2 says that if you have such a test, then for any APN that is epsilon delta stable, the power of this test is bounded from above as the smaller of 1 and alpha raised to the power of 1 minus delta epsilon star over 1 minus delta raised to the power of kappa, where kappa again is this fraction. So equation 2 looks a lot like equation 1, the right-hand side of equation 1. The only difference is that the exponent here is kappa and the exponent here is k. But k is the floor of kappa. Okay, why should such a bound hold? So this is like a very brief sketch of our argument. The details are in the archive draft of the paper. The proof is based on constructing a perturbed triple A prime P prime N that satisfies certain properties. First of all, the most important thing that this construction is designed to satisfy is that this triple is not epsilon delta stable. And this is useful because because the test is to control the type of error for all learning algorithms and all data distributions. In particular, it has to control it for this A prime, P prime, and N. So if the test is applied to A prime and data sets drawn from P prime, it outputs 1 with probability less than or equal to alpha. However, because we're going to make A prime quite similar to A and P prime quite similar to P, we're going to limit it in distinguishing the outcomes, the predictions that you produce by applying data from P through putting data from P through A and putting data from P prime through A prime. And this gives you a way to relate the bound on the probability of reduction for the original triple using the bound and the probability of reduction for this perturbed triple. A prime is supposed to be similar to A in the following sense. If we use data from P and not P prime, and then we give them to A prime and A, it's supposed to result in the same outcome with probability 1. In particular, if we apply the test to data from P, we get the same answer with probability 1, whether we use A prime or A. So this statement holds. In the case of P prime, we're going to use a mixture of P and some other probability distribution P1, and with some choice of mixing coefficient C. This allows us to construct a coupling of data sets from P prime and data sets from P, because you can think of sampling from P prime as first sampling from P and P1, and then flipping a coin to decide which sample that you're going to keep. So probability that the two data sets match is lower bounded by 1 minus C raised to the power of NL plus NL. We are also going to consider a special case in which the marginal of P prime and P over just the distribution on the features, the axis, is the same. In that case, the difference is only in the labeled data and not in the unlabeled data. So the lower bound becomes 1 minus C raised to the power of capital N over L. Okay. Now, suppose I can do this construction, satisfying these 3 conditions. Then this is how I relate. This is how I end up with the bound and the power for this test. First, I have that alpha is lower bounded by the probability that the test results when it's applied to A prime and data sets from the perturbed data distribution. This probability is obviously lower bounded by the probability that the test outputs a reduction using A prime and data sets from P prime, and the data set from P prime is equal to the data set from P in the coupling. Because on this event, the curly D primes are equal to curly Ds without the prime. I can replace curly D primes in that's being fed to the testing procedure by the unprimed ones. I can obviously rewrite this as the product of these 2 probabilities. Now let's look at the first quantity. Because of the assumption that I made about A prime, I can replace A prime with A. These 2 probabilities are the same. As for the second probability, this is lower bounded by 1 minus C over capital NL plus NU because of this. And in the special case that I have, well, P prime and P have the same marginal distribution over X. The lower bound is actually 1 minus C raised to the power of capital N over L. Now, combining the this inequality and this, and then rearranging, I get that probability that the test outputs a reduction when applied to the original learning algorithm and data sets from the original data distribution is upper bounded by alpha over 1 minus c raised to the power of capital NL plus capital NU, or alpha over 1 minus c raised to the power of capital NL when the mixture happens to be 1 such that the marginal distributions over X are the same. So what I have shown so far is that if I'm able to do this construction, if I'm able to construct a perturbed triple that is not epsilon delta stable, and it satisfies these 2 additional conditions with some mixing coefficient C, then this implies this bound power for the original triple. It turns out that the construction is possible for any C such that C is greater than 1 minus delta over 1 minus delta epsilon star raised to the power of 1 over n plus 1 in the general case, or C greater than 1 minus delta over 1 minus delta epsilon star over 1 over n in the case where the marginal over x's are the same. So the rest of the proof is about doing this construction, and that the construction is where we needed a good formal definition of black box testing procedure. We use it to define P prime as well as A prime, and then we also needed to check the condition that this condition on A prime is satisfied.
I think it's already 4:30, so you might want to end the talk.
Okay. Okay, so interpreting the 2 theorems, on the one hand, I got from theorem 1 that for the simple binomial test, if delta is less than or equal to 1 minus alpha raised to the power 1 over k, then I have this bound on power. Well, I have this expression for power. Theorem 2 gave me a bound that applies to any black box test with assumption-free control of type 1 error. And in the case where kappa is an integer, then these 2 bounds are exactly the same. So in that case, the simple binomial test achieves the best possible power for all black box tests with assumption-free validity in spite of its utter simplicity. This is surprising because we would have hoped to improve power by making additional runs and resampled or simulated data. So yep, this will be my last slide then. So you might wonder if this is a bad pessimistic result. And it depends on how you're trying to, why you might be interested in measuring stability in the first place. So if you're interested in measuring stability, it's because you want to apply it to some downstream method. You're checking assumptions for some applicability of some downstream method. Then you probably want to use all the data points that you have available for fitting a model for the greatest possible accuracy. In that case, you probably want to set the sample size at which you want to measure stability, small n, is probably equal to capital N of L. Then k is exactly equal to 1. So theorem 2 tells you that you are severely limited in your ability to make accurate inferences about the stability of your learning algorithm in this black box setting. However, if you might be in a setting where you have to come up with a novel method, and then it's really complicated, so it's really hard to do a mathematical analysis. However, you might still want to provide a stability profile as a part of a theoretical investigation. Then you might have the freedom to choose n, and you might even be able to choose it so that the ratio kappa is large, in which case you can obtain accurate estimate about the stability of your learning algorithm. And this is a summary of what I've discussed in this talk. And here is the address for the archive article. And thank you.
I'm sure we probably can have like one quick question. So, any questions?
So I have one hopefully quick. So it's very interesting to look at this kind of in general cases like what you did, but what happens if you apply this to a well-known parametric model like linear model? What does this metric of stability look like?
So in that case, you can probably do better. So this is actually one of my questions, well, for future directions. If you're in a situation where you can use you're able to analyze the models very well, and the algorithm is very complex, then it's like you have infinite amount of data for studying fitted models. So your bound should no longer depend on the number of unlabeled data points that you have. So yeah, you can use that knowledge.
Okay, so yeah, okay, so I think because of the time constraint, I think we have to end now. So thanks everybody for participating. And if you have further questions, feel free to reach out to Byol. Okay. And thanks Byol for a really nice talk.
Thank you so much. This is exciting. Do I stop? Oh, there's like.
I think I can. I'll just end the meeting.